Hello, welcome again. We'll continue our discussion on engineering thermodynamics. So now we'll continue our discussion on second law of thermodynamics. In this session, let us define absolute thermodynamic scale, establish relationship between Kelvin, K, and degree Celsius, define efficiency of reversible engines in terms of temperatures of source and sink. We will define COP of heat pump and heat engine in terms of temperatures of source and sink. First, let us go for absolute thermodynamic scale. Here I have shown a coordinate system. This is some thermometric property. For example, if you are using mercury in glass, so when you dip the mercury thermometer in a hot bath, the mercury column rises. Then length of that mercury column is what you call it as thermometric property. Similarly, if it's a constant volume thermometer, when you dip this thermometer into a hot bath, its pressure increases because volume has to remain constant. Then that pressure is the thermometric property. So suppose, let us say, I have a glass thermometer. I might use water as a thermometric substance, or I might use mercury as the thermometric substance, or I might use alcohol. Suppose if I use water thermometer, the thermometric property versus temperature characteristic, if I draw, I'll be getting a characteristic like this. Instead of water thermometer, if I use mercury thermometer, then the characteristic may be something like this. If I use alcohol, then the characteristic may be something like this. Suppose I want to measure a temperature, let us say something like 35 degrees Celsius. 35 degree. This is the 35 degree. If I draw a vertical line, okay, this is what the thermometric length for water thermometer. This is the thermometric length for mercury thermometer. This is the thermometric length for alcohol. They are not showing the same this thing, right? Suppose if I take one particular thermometric value length, then this thermometer will show one temperature, this thermometer will show some other temperature, this thermometer will show some other temperature. That means to say, it all depends upon the thermometric property. So I want to have a thermometer which is completely independent of this thermometric property. Such a thermometer, I call it as absolute thermodynamic scale. See here, the thermometers which are constructed using physical properties of substances have got many drawbacks. The different thermometers may read different temperatures except at the fixed point here and here. This may be ice point or triple point of water. This may be steam point. At these 2 points, calibration points, they read the same value, but in between they read some other value. The different thermometers may read different temperatures except at the fixed point at which these are calibrated. Because the actual relationship between the thermometric properties of the substances and temperatures, as I explained, volume, temperature, pressure, temperature, resistance temperature relationship may not agree at all points on the scale as shown in figure. So different thermometers read different temperatures in the intermediate region depending upon the properties of the substance used. I have clearly explained this on this coordinate system. So the extrapolation also may be erroneous. Hence, it is necessary to have a device which would read the temperature without being affected by the property of the thermometric substance. Such a device can be developed by using the concept of reversible engine. So a temperature scale which is independent of the thermometric property of the thermometric substance is defined as thermodynamic temperature scale. So a temperature scale which is independent of the property of the thermometric substance is defined as thermodynamic temperature scale. Now let us develop a relationship between source temperature and sink temperature with respect to heat supplied and heat rejected. Heat supplied from the source and heat rejected to the sink. Let us develop that relationship. You know, the efficiency eta for a reversible heat engine is equal to W net by Q1. Q1 is the heat supplied from the source. W net, as I've already explained, it is Q1 minus Q2. We can write this as 1 minus Q2 by Q1. This is the efficiency of a reversible heat engine. So from second law, we have understood that it is necessary to have a temperature difference T1 minus T2 to obtain work for any cycle. So we know that the efficiency of all heat engines operating between the same temperature levels is the same from Carnot's theorem, and it is independent of the working substance. Therefore, for a reversible cycle, the efficiency will depend solely upon the temperatures T1 and T2 at which the heat is transferred. Hence, we can say efficiency eta reversible is equal to function of temperature of the source and temperature of the sink. That is, efficiency of the reversible engine is always a function of temperature of the source and the temperature of the sink. So the function word, so I have just denoted by small f. In mathematics, the function is always denoted by f. So now we can say 1 minus Q2 by Q1 is equal to function of T1 and T2. Maybe I'll remove this 1 minus Q2. I'll simply express Q2 by Q1. I'll use some other function ft1 comma T2. It is just an equation. Function in the sense it is a relationship, a mathematical equation. So if some functional relationship is assigned between T1 and T2 and Q2 by Q1, the equation becomes definition of a temperature scale. So assume that there is a reversible engine. It is working between the temperature range T1 and T2. Then I can write now Q1 by Q2 is equal to function of T1 comma T2. You consider another engine working between the temperature T2 and T3. Q2 by Q3 is equal to F T2 by T3. Say I can show like this. You have a source. Here there is another this thing. Then another temperature. Heat source. There is an heat engine. There is an heat engine. Let us say this temperature is T1. This temperature is T2. This temperature is T3. This engine is working between the temperature T1 and T2. That is Q1. This is Q2. This engine is working between T2 and T3. That is Q2 and Q3. Suppose I have another engine working between T1 and T3. This is a Q1, this is Q3. Now I can write Q1 by Q2 is function of T1 and T2. Q2 by Q3 I can write function of T2 and T3. Now this, if you take, I can write Q1 by Q3 is equal to FT1 comma T3. This can be written as Q1 by Q2 divide by Q3 divided by Q3. Then you can write like this. So now Q1 by Q2 we can write it as FT1 and T2, taking out the common term. So Q1 and Q2 FT1 comma T2, or you can write some other function phi T1 phi T2. So phi of t is an arbitrary function. This can be read as phi of t1, phi of t2. It is some function depending on temperature t1. There is some other function depending on temperature t2. So in general, t can be represented as phi of t. Say phi of t is equal to t as proposed by Kelvin. Then by definition, we can write Q1 by Q2 is equal to T1 by T2. The absolute thermodynamic temperature scale is also known as the Kelvin scale, right? And it is independent of peculiar characteristic of any particular substance. So that is what we call it as an absolute thermodynamic temperature scale. Let us develop a relationship between, and that absolute temperature is always represented by K, Kelvin. And let us establish a relationship between K and degree Celsius. Let us write an equation, temperature of steam point and the temperature of ice point. Or you can call it as triple point of water also. Ts minus Ti, this value is equal to 100. Now efficiency of a reversible engine now, eta R is equal to 1 minus, I can write Qi by Qs, that I can replace by Ti by Ts. You know this is Ti value, the temperature of triple point of water, and this is steam point, and the efficiency of such an engine is found to be 26.8%. That is 1 minus Ti by Ts is equal to 0.2680. So this is an experimental value. So now the question is, from here you get one equation relating Ti and Ts. Here we have Ti and Ts, another relationship. Solve this, we will solve this equation 1 and equation 2, and you'll be getting Ts value is equal to 373.16 K and Ti is equal to 273.16 K. This is nothing but ice point. So 0 degree Celsius. This is always equal to 273.16 K. In general, Kelvin is equal to any degree Celsius plus 273.16. Suppose 10 degrees Celsius is the temperature indicated by a thermometer. This on absolute thermodynamic scale given as 10 plus 273.16, that is 283.16 K we write. We don't write it as degree K, simply write it as K. It is impossible to attain 0 K on Kelvin thermodynamic scale. That's what we say. Now, if you take the efficiency of a reversible engine expressed in terms of TL and TH, if I put TL is equal to, let us say 0. 0 by something is 0, then it is equal to 1. That means to say it is 100% efficient. 100% efficiency is nothing but what? It is violation of Kelvin Planck statement. Correct? That means it is impossible to have an engine of 100% efficiency. Hence, it is impossible to attain 0 K on Kelvin thermodynamic scale. In other words, it is impossible to have a system whose temperature can be 0 K. That means completely you remove every substance, everything present over here. I think it is impossible to do that. Now let us express efficiency of the reversible heat engine in terms of temperature of the source and temperature of the sink. Efficiency of reversible engine, eta reversible, it is always maximum efficiency. 1 minus QL by QH. QL by QH for a reversible thing, I can say that is also equal to TL by TH. So we can write now the efficiency of a reversible engine is equal to 1 minus TL by TH. Please remember we are using the symbol capital T. So always you have to express temperature in absolute scale in Kelvin. Correct? Similarly, for a heat pump, this is refrigerator, the purpose is to achieve QL. This is the work supplied. Reorganizing, you will be getting COP refrigerator as TL divided by TH minus TL. Same way, COP heat pump, our objective is to keep the temperature of the system higher than its surroundings. Then this is what reorganizing, replacing QH by TH, QH by QL by TH by TL, we are going to get this COP of heat pump. Please remember that these relationships hold good only for reversible cases, ideal cases. In an actual case, we should not be writing like this. This we will study little later. How do we do it for an actual engine? It is always for reversible engine. In conclusion, under second law, we have understood or explained the concepts of heat engine, heat pump. We define first law efficiency, COP. We stated Kelvin Planck statement and Clausius statement of second law, and we also proved they are equivalent. Explained the concept of reversible engine, irreversible process. Why a process becomes irreversible, that is also explained. Internal irreversibilities and external irreversibilities also we have understood. Then we have stated Carnot's theorem and we have proved that. And also we stated corollary to Carnot theorem and proved that. Then based on that, we defined thermodynamic temperature scale and we expressed the efficiency and COP of heat engines and heat pumps in terms of temperatures of source and sink. Hope you have understood all these concepts well. We will solve some examples based on that in the next session. Till then, thank you very much.